Hello everyone. In this video, we are going to talk about the last type of gear that we haven't discussed so far, and that is the worm gear. So if you look at the worm gear, it is basically similar to a screw or a bolt, right? So it has a bunch of basically thread features, and it is meshed with this gear, which is called the worm wheel, and they work together. Okay, now they have some important properties that makes them really great. Now, by the way, there is another type of gear that I never discussed, and that is rack and pinion. Now, rack is basically a gear with teeth like this, and that is a flat type of gear, and the pinion of that is something similar to this wheel, right? So the thing about rack and pinion is it converts the circular motion or rotary motion into linear motion and vice versa. And you use it a lot when you want to have a linear motion controlled by a motor or a stepper or DC motor or stepper motor or anything, like in 3D printers or so many other places. So that I have not discussed, and I don't think it needs a separate video of its own. So here, this is kind of different. The fact that this gear is kind of straight, that is different from the rack. For rack, the teeth are on one side. Here, the teeth are like threads, basically. Okay, so rack, which is this guy here, that is a complete different thing compared to the worm and the worm wheel. First of all, the worm and the worm wheel, they convert rotary motion to rotary motion, okay? So here, the worm is spinning, and that is going to cause basically the wheel to spin. So it's a rotation to a rotation. But the axes, if you look at the axis of rotation, here is one of the axes, here is the other one. You see that the axes are askew. So a worm and a wheel are used to transfer powers between skew axes, okay? Which I mentioned here. Now, is that the important property? No, because as you know, helical gears can do the same thing. So why do we go with this kind of gear? The major reason for it is huge gear reduction in a compact space. For instance, if I want to go from, I don't know, 1,000 RPM to 10 RPM, right? I want to reduce my RPM by a factor of 100 to 1. Then if I want to go with simple spool gears, the way to do it is, if I want to do that, then one of these gears have to be 100 times bigger than the other one, right? Because the speed ratio, which is in this case, is basically the input, which is 1,000 over output, which is only 10. So this guy goes 1,000 RPM and this guy goes 10 RPM. Then this is equal to the ratio of the diameters, right? So this is equal to, if I call this gear 1 and I call this gear 2, so this is like D1 and this is D2, that is going to be D2 over D1. So you see that one should be 100 times bigger than the other one, or it has 100 more teeth compared to the other one. And that will make one of these gears to be super giant. And if that's the case, then you need a big space to put these into it. So instead of doing something like this, they do it in multi-stages. So they don't directly go from 1,000 to 10. They don't directly go by a factor of 100 in one step. They do it in several steps. So for instance, first they have this gear here. That is, I don't know, this is something like, for instance, 5 times bigger, right? And then here, the RPM of this guy is going to be basically 200 RPM. Then they attach another small gear rigidly to this big gear. So this one and this one, gear 2 and 3, are rigidly connected. And then they connect this gear 3 to another big gear like this that is 5 times bigger. So the small gear and the bigger gear number 2, these two, if I call this D2 and this one D3, omega 2 and omega 3 are both equal to 200 RPM because they are rigidly attached. Then they go with this D4, which is 5 times bigger than D3. So now the RPM goes down from 200 to 5 times smaller. So now it is going to go to 40 RPM. And then they connect another gear and rigidly attach it to gear number 4, call it gear number 5. And that gear number 5 is now attached to another gear. This gear number 6 is gonna have a reduction. So this is like a 5-to-1. This is another 5-to-1. This last one is like 4-to-1. So you go 40 RPM to now 10 RPM. So that factor of 100, which is this ratio, you break it into 3 stages. One is 5, the other one is 5, the other one is 4. So you do a multi-stage, and this is how many gearboxes work. Now, of course, in this direction, in this X direction here, you need quite a bit of space to include all of those gears. If you don't want to do all of those gears, which equals space and equals cost and money, you can only do it with a single worm and a single worm wheel. These guys can reduce the RPM by factors up to like 100-to-1 or even more in a compact space, and so they can also transfer big torques. Now you might say, how come? Well, per one full rotation of worm, when this worm goes one full rotation or 2 pi radians rotation, guess how much this will move forward? Because the teeth of this wheel are being pushed by these threads, and the amount of displacement for each thread is only 1 pitch, correct? When you rotate it 2 pi radians, it only moves by 1 pitch. And since each one of them is in contact with one of the teeth here, all you will get here for the rotation is simply 1 tooth. So all this guy will rotate is going to be 2 pi divided by the number of teeth. So you see the ratio is going to be n-to-1, where n here is the number of teeth on this guy. So if this guy has 100 teeth, guess what? Your speed ratio is going to be 100-to-1. And it does it beautifully, okay? So that is the first thing, huge gear reduction. The second important property is self-locking and one-way rotation. In this system, only the worm can spin the wheel. The wheel, if wheel tries to spin, the worm cannot be spinned, okay? Because the teeth cannot push those, cannot create a torque to spin the worm, okay, for those threads. So only the worm spins the wheel, not the other way around. So you can use them for self-locking mechanisms. Like for instance, in musical instruments, if you look at them, you clearly can see the wheel and you can see the worm here. So when you spin, when you rotate these tuners, right, these tuner pegs, then they basically spin the wheels, and the wheels are attached to these strings. So by turning the worm, you can add or reduce the tension inside those strings, which by itself changes the frequency of them, so you can tune the device. Okay, but once you put them in a position, once you give them so much of tension, you know, these guys have tension. So can that tension pull back and causes this wheel to rotate, and the wheel causes these pegs to rotate? No, because it's a one-way rotation. So that tension, although it exists in the string, it cannot cause these pegs to rotate backwards and release that tension. There is no way. Or let's say if you have a lift mechanism, right? If you have any lifting elevator lift mechanism, so what you can do is here, let's say connect this axis that this wheel is connected to. Let's say you connect it to some load. Okay, and this is a rope. So as this guy spins, this rope that is connected here starts to wrap around this shaft, and so this object goes up. Okay, and this is causing by the spin of this worm, which can itself be connected to a motor. Okay, so it can be connected to a motor, and the motor spins the worm, and the worm spins the wheel lifts up an object. Now, if motor goes off for a minute, what's going to happen? The torque that was applied to the wheel, the worm, is going to go to zero. So there will be no torque on the worm, there will be no torque on the wheel. And that was the torque that was lifting this object up. So when the torque goes away, can this object now fall down under its own weight? The answer is no. Because as soon as it wants to do it, that means this wheel has to rotate backwards, and that means now the wheel has to rotate the worm, and guess what? It cannot do that. So it is going to lock in place. Okay, so this is another extremely important thing. The other thing is they are relatively smooth and quiet, but the bad thing about them, so these two are great. The bad thing about them is their low efficiency. Why? Because here you have a tooth against a thread, and the contact here is pure sliding contact. And because of the friction between the two metals, the efficiency of power transmission is low. It's typically 20 to 50%. So if you use, I don't know, let's say if this motor is 1,000 watts, right? The power that you get out of this wheel could be, for instance, 300 watts. And the power here is equal to is the torque that you get out of it times the omega that you get out of it, T times omega. Right? So only 20, 30, up to 50% of the power in is going to be your power out. That is the efficiency that the system has due to big friction. Some of the applications of them, as I mentioned, are in conveyor systems, in elevators and lift, in tuning instruments, in gate and valve actuators, in rotary tables, in CNC machine, and in hoist and jacks. Okay? So the most important properties, as I said, are huge gear reduction and the self-locking. Okay? These are very important. So that's why you typically see them a lot after motors, because motors have huge RPMs and we don't need that much of RPM. So this guy is spinning like 10,000 RPM. I want to bring it down to maybe 100 RPM. And instead of a multi-stage gearbox, I use just one of these. The other thing it can give me is the self-locking, which could be very useful, especially, as I said, in elevators, lifts, hoists, and jacks. These are very useful. So now let's look at some parameters of these worm and the wheel. Let's look at some kinematics parameters, and then force analysis, efficiency, and transfer of torque. There are a few things that we need to care about them. And then finally, as a bonus, I will solve one problem involving worm and the wheel for you, so you know how to basically deal with problems here. And as my previous videos, the material is coming from Shigley, Mechanical Engineering Design. Okay, so now that we know it, let's go ahead and look at some of the parameters involving these kind of gear. What do we have? So here is a picture of a worm from the side view and the front view, and this one here in gray is the worm gear, or the wheel, you might call it. So what kind of parameters do you have? As I said, the worm is kind of similar to a thread, so you can expect it to have something called an axial pitch, which is the distance from one tooth to another or one thread to another. That's called axial pitch, px. Okay, that's the first thing. The second thing that you expect to have is different diameters. Now, the diameter that we care about here is the pitch diameter. That's one of them, which is the diameter of the circle here that touches the circle of the other one, tangent with it. And you could also define a root diameter, which is the distance from root of the tooth to root of the tooth. You can similarly define a maximum diameter here, okay? But the one that we really care about is this one, pitch diameter, d of the worm. The other thing is these threads are on a helix, so you definitely will have a helix angle. Helix angle, or psi, is defined as the angle between the axis of the worm and the tangent to one of the threads or one of the teeth. Now, the angle that this tangent to the thread makes with the vertical axis, on the other hand, this angle, we call it the lead angle, or lambda. So in this picture, you can see that lambda plus psi is equal to 90 degrees. Okay, so you either make the angle of the surface with the axis of the shaft or with the vertical to that. And you call it either lambda or helix angle, either lambda or psi. The other thing itself is the lead. This lead here is basically the amount that is, if you look at it, let me clean this so you can see lead better. The lead here is defined as basically the distance you have between two similar points. So it's the distance from here to here. And you might say, what is the difference between lead and the pitch? Because they kind of look similar. Well, the answer depends on how many basically threads are there per one revolution. If in one revolution you only have one tooth engaged, then yes, lead and pitch are equal. But if you have more than one thread in the worm that is causing the linear motion, and you show that by NW, the number of threads or the number of teeth that it has, so then the number of teeth times this pitch is going to be equal to the lead. So lead is the amount of linear motion along the axis per one full revolution. Pitch is the distance between two similar points on the one tooth and the next. They are equal if there is only one tooth on the worm, but most of the time there is more, and you have several basically threads that go around, and you can say that NW times P is equal to L. So this animation can show you better, and this is about the threads. So in the bolts and nuts, we have the same distinction. Again, lead is the amount of axial advance per one full revolution. Pitch is the distance from one point to the next similar point. So if you have a single thread, then, as I said, they are exactly equal. Lead and pitch are the same. But if you have a double thread, like this case, right? So this blue one is one thread and the green one is another thread. So when you go one full revolution, look here, it moves like two pitches as opposed to one. And here, that is four threads. Then per one revolution, you are going to move 4 pitches forward. Okay, so this animation can very clearly define the difference between lead and the pitch. Okay, so these are the parameters involving the worm, dw, px, L, psi, and lambda, or psi or lambda. For the wheel, we have its own pitch diameter, which we can show by dg. And you can treat this like any other gear. For instance, the d, the diameter of this pitch circle here, can be defined as n, the number of teeth on it, times p. This p is the circular pitch in the transverse direction for this gear, and divided by pi. Because if you remember, p, the definition of it, p transverse, the definition of it was basically pi times d divided by n. So if you solve for d, it's going to be pn over pi, right? So the formula that you had for the spool gear still valid here. Now c, the center to center distance, is the distance from this point to this point here, right? That is your c. And clearly you see it is this distance, which is half of dg, plus this distance, which is half of dw. Okay, so that is similar to any other two gears. Center to center distance is always the average of the two diameters. Okay, that's basically the same thing. Now, one thing here, one formula that is common for these worms and wheels is this formula. It says if you want to pick a number for the diameter of the pitch for the worm, make sure it is between c to the 0.875 or 7 to the 8 divided by 3 and c to the same power but divided by 1.7. So if you want to pick a worm and you want to know the size of that worm or the diameter of the pitch of that, based on the center to center distance, this is the kind of good range to pick. And you might say, where does that come from? If you pick it in this range, you can optimize this efficiency number. So if you want to get bigger efficiencies, you have to pick a DW in that range. If you pick it outside the range, you are going to get lower efficiencies. Okay? And this is an empirical formula, clearly. What else do we have? The speed ratio is clearly the omega of the worm, because worm is the driving always, over omega of the wheel, which is the driven, and it simply can be written as the number of teeth on the wheel divided by the number of teeth or thread on the worm. Okay, so the same formula that we had in the spool gears, it also again applies to the worm and the worm wheel. So if I here only have a one thread and here I have 100, as I said, you get a speed ratio of 100 to 1. The next thing you have is the relation between this lead angle and the lead itself and pi dw. So here, if you unwrap one of these teeth as it goes around, if you unwrap it, okay, if you unwrap that, you see that basically you're going to get something like this. The total distance traveled by any point on one of the teeth is going to be pi times dw, right, the circumference. The distance that you move in the axial direction when you go around one of these teeth and come back, the only left and right or axial motion that you have is the lead, and the angle that you have is the lead angle lambda. So clearly you see that tangent of lambda is the lead over pi dw, and that's where you get this formula. So if I have the lead and if I have the d of the worm, I can find the lead angle. And once I have the lead angle, I can also find the helix angle, right? So these are the important parameters and formulas involving worm and the wheel. Now, what about the force analysis? So force analysis is quite a bit interesting. Why? First of all, between the tooth of the wheel and the tooth or the thread of the worm, there is a three-dimensional force exchanged. which has three components. It has this vertical component y, which is like a radial component. It has the other radial component x, and it has an axial component z. Now, between these, the x component is, although it's radial, but it's also a transverse component. So x is the one that is gonna create the torque. So x is the one that is creating the torque, right? You can see it here. Wx is the transverse component. Y is the radial component. And z is clearly the axial component for the worm. Okay? So this is the force, this is the normal force between the two teeth. But that's not the only force. Remember, I said that here you have friction. The tooth of the worm and the wheel are sliding against each other. It's all about sliding contacts. Okay? So there should be some kinetic friction force as well. And this guy here is your kinetic friction. So you have two major forces. One is the W or the N force, the normal force. And the other one is the friction. And these are just their components. So which direction is the friction? Of course, the direction of the friction, if you look at it, it is tangent to the helix. It is tangent to the tooth profile, right? The tooth or the thread of the worm. So it is tangent to that. It is in that plane. So I can break it down into two components. One that is in the axial direction and one that is in the transverse direction. So my friction force, which is F, here this F acts like mu. This is the coefficient of kinetic friction, or mu k. If I multiply that by the normal force, and W here acts like N. So the product of them is the kinetic friction, Fk. So in other lectures of me, you see I say Fk equal N mu k. Here it says Wf equals F times W. But that's the same thing. This is kinetic friction. And you have two components, a sine lambda and a cosine lambda. Why? Because this angle here is your lambda, okay? That is this same lambda angle, and you know that lambda is the angle that your helix is making with this vertical direction, and that is exactly what you have here. This is that vertical direction, this one, and this is the direction of tangent to the tooth, so that is your lambda. So here you have these two components. Now this tangential transverse component, Fw cosine lambda, this is added to that Wx. So you see that, you can see it here, look, this is this guy. And this one, which is the axial component, this is in the opposite direction of W, so it should be subtracted from that. And that is what you can see here. So those two components that you see, those plus and minus F W cosine lambda, those are the friction components. Now, what is the rest of it? The rest of it are clearly these guys here, this W sine phi n sine lambda, W sine phi n, and W cosine phi n cosine lambda. These are your W, X, Y, and Z in this picture, and you can clearly see why. Because your W has this angle phi n, which is your normal pressure angle, and it has this angle here, lambda, correct? So when you want to decompose this W along X, Y, Z, you have to use sine phi n and cosine phi n, and then sine lambda and cosine lambda. So you get these three forces, and as I said, these three forces, the X one is the transverse one, that's the one that transfers the torque. The Y one is the radial one that is applying to the bearing, and the Z one is the axial one that wants to move the worm left and right. So you need to have some bearing on this side or this side that has an axial load and doesn't let the worm move. Okay, so you see that the formulas for the force in a worm is quite a bit involved, and I just explained that to you. Now let me show you this middle part here. What is this middle part? Let me explain that. By the way, the transverse component of the force for the worm, which is this guy here, as I said, this is the one that transfers the power or torque. So you can find it by the same formula that we had in spur gears, and that was 33,000 times H over V of W. H here is your horsepower. This is the horsepower applied to the worm, right? And this is the velocity of the contact point, right? So this is the velocity of the contact point or at the pitch circle. And this is, of course, for the worm. How do I calculate that? I'm going to show you. The formula is exactly similar to the spur gears, okay? So it is coming from basically a pi dn over 12. So we're going to see that. Now, let me, as I said, explain this middle part here. So if you look here, it says that the transverse force for the worm is the axial force for the gear or the wheel with a negative sign. Where does that come from? Where here you need to add a gear like this, the wheel, and what's going to happen here? These are the threads, and this guy is spinning like this. So let's say it is pushing this guy forward and it is spinning like this one. So for this one, because the axis of this is in this direction, the axis of the gear is like the x-axis for the worm. So any force that you have in the x-axis, which is basically your transverse force for the worm, is going to count as the axial force for the gear, right? Because it's action and reaction. So if the gear applies Wx to the worm, the negative of Wx is going to be applied to the gear. And for that, as I said, this is the axis of it. So that's where this one comes from. That the axial force for the gear is the transverse force for the wheel, except with the negative sign. Why negative sign? Because of the action and the reaction, of course. Good. What about the radial force? Well, when you apply this Wy, then the opposite of that is going to be applied to this. So it is going to be Wy like this. And clearly, this is the radial direction for that. So the Y, which is the radial direction for the worm, is also the radial direction for the gear, except with a negative sign. And that is this guy here that you can see. Finally, the Z component of the worm that is along its axis, the opposite of that is applied to this guy. So here you're going to get a WZ like this. And this one is the one that is causing rotation of the wheel. So clearly for the wheel, it counts as the transverse component. And that is this last one that you can see. Now, I did this one wrong. So if the WZ is to the left, then clearly the rotation of the wheel has to be this way. Because this WZ is to the left, the torque of it for the center is going to be this way. So this is going to be N of the gear. And small n here means RPM. It's not the big N. Don't mix them together. Big N is the number of teeth. Small n is like omega. It's like RPM. Okay? So this is the decomposition of forces. Now, there is one more thing I want to show you, and that is the efficiency. As I said, because of the existence of friction, the power that you apply to the worm is not going to be all passed to the gear or to the wheel. Some portion of it will, because you have friction. How do I find that? Well, here I need to define the efficiency. Efficiency is defined as the transverse force that is in the worm if there was no friction divided by the transverse force that is in the worm if there is a friction. And you might say, where does that come from? Because remember, power is defined as force times velocity. In this case, Wt times velocity. Right? So you can say W of Wt if you want to go with that formula, with that notation. The force for the worm in the tangential direction times velocity. Now, when there is friction, if you keep this V constant, then you see that P is proportional to that tangential force. So if you keep the RPM constant for the worm, then you have to lose some force acting on it because you are losing power. So I can say the power is proportional to what? To the transverse force. And so the case that it has no friction to the case that there is friction, I can call that ratio the efficiency. Now, how do I get that? For that, I need to find a formula for W of Wt. How do I do that? Well, that is not super hard to do. Why not? Because all I need to do is to divide this first formula by the last formula. So if I call this relation 1 and this one 3, all I need is to divide 1 by 3. If I do that, these two W's would cancel. You get Wx over Wz is going to be this guy over this one. Now, what is Wx? Wx, based on the definition, is the worm transverse force. And Wz is what? Wz is negative of the transverse force in the gear or in the wheel. So basically what I can do is first I need to negate 3, so I get positive Wg t and then divide. So instead of saying 1 divided by 3, it's better to say 1 divided by negative of 3. So first negate 3, then divide, and from there, guess what? You can get this equation here. Now, what's so special about this equation? In this equation, we found a formula for force, transverse force in the worm without involving W because we don't know W. Okay, now what? Now I can use this formula here. One time without friction. What does without friction means? Means get rid of F. Remember, F is your friction term. So in one of them, get rid of F. So you get WGT cosine phi n sine lambda over negative cosine phi n cosine lambda. And these guys can cancel out. Yeah? In the other one, do include the F because it's with friction. And simplify it and you get this beautiful formula if you do a little bit of algebra. So the efficiency is equal to cosine phi n minus F tangent lambda over cosine phi n plus F cotangent lambda. And this is the formula for efficiency in a basically worm gear. Now, what parameters are involved? The first one is the coefficient of friction. Clearly, when this guy is bigger, when this F goes up, what's happening? This negative term gets bigger, so the whole numerator drops. The denominator gets bigger, so the denominator goes up. So you can see clearly the whole thing drops. So bigger friction means a smaller efficiency, and it's kind of obvious here. What about this guy? This one also has effect. The pressure angle has some effect. The other parameter that has effect is the lead angle, lambda. And lambda is a function of what? If you look at it, lambda is a function of lead and is a function of diameter of the worm, diameter of the pitch circle for the worm. Okay, so from these two, you can find a formula for lambda. which is like arctangent of pxnw over pdw, right? There we go. And we're going to use this formula in the example that I'm about to solve. So you see, the way that I can affect the efficiency is clearly I can change the size of the worm, I can change the number of threads on the worm, I can change the circular pitch on the worm, I can change the friction coefficient, and I can change the normal pressure angle. Okay, all of them can be done. And by the way, the relation between phi n and phi t, if you remember, if I go back and show you the helical gears, let me show you that. So there was a relation that we had between phi n and phi t, which was by cosine of psi. The same relation exists here. Okay, so still tangent phi n equals cosine psi tangent phi t. Okay, so these two are still what? Related, because you can see both of them also here. You see phi t and phi n. So I can still say that, tangent of phi n equals tangent of phi t times cosine of the psi, and psi here is that 90 degrees minus lambda, or that lead angle, that helix angle that you have. Okay, so you can still use this. By the way, this is t, okay, that's not a plus. So this is times cosine psi. So all of those formulas are valid, and again, I'm going to use them. Now, one more delicacy that is there is this friction here, this coefficient of friction. Is that a constant number? So for instance, if you have one worm and a wheel from two different material or the same material, is this coefficient of kinetic friction a constant number? The answer is not really. The coefficient of kinetic friction does depend on the relative sliding velocity. The faster the worm moves against the wheel, the smaller this kinetic friction is going to be, and vice versa. And you can see that here. This is F versus the sliding velocity Vs. The bigger the Vs, the further this guy drops. Now, it's not going to be a big drop, but still it's considerable. So if you might start at 0.08 and you might end up at like 0.03 or something, depending on how fast in feet per minute this guy goes. And these guys are basically empirical curves. The first question is, even if I given a curve like this, where do I find this slide velocity? The slide velocity, you can show that the slide velocity is given by the worm velocity, Vw, over cosine of lambda, cosine of the lead angle. Now, what is the worm velocity? As I said, the worm velocity is the formula that we had in spoor gears. It was pi d of the worm, n of the worm, divided by 12. And this n here, pay attention, this is the RPM of the worm. It's not the number of teeth. This is small n. So if I find the velocity of the contact point here of the worm and plug it right up there, I can find my slide velocity, and then whenever I have it, I can come here and say, well, I have 900 feet per minute. I go to this curve, and then I project it here, and maybe, I don't know, 0.035 or something. Now you might say, why are there two curves? Each one of these curves is for a different scenario. So these curves, these guys are all coming from Shigley. Let me tell you what is curve A, what is curve B. Curve B is for high quality material. Like if you have a worm that is made of steel that is case hardened, and the gear is made from a phosphor bronze. So this guy is really hard. This guy is amazing against wear and tear and sliding. So they work great together, and you see their material are different. So you can use, for this high quality material, you're going to see that you have used curve B, which has a smaller friction. Curve A is where your material is not as good. You can have more friction. Like for instance, your worm is made of cast iron and your worm is also made of cast iron. Okay, so the surfaces are not that beautiful. The material have more friction in them. So then you can use curve A. So curve A, more friction, lower quality material, high friction material. B is better material, smoother material, low friction material. Okay, so these are these two empirical curves. Now, the last points before we go over the example. 1, how much torque are you get out of the wheel or the gear? The torque that you will get out of the gear is going to be the speed ratio times the torque that you apply to the worm. This is your input torque. This is your output torque. Ideally, the ratio between them should only be equal to the speed ratio, because the speed ratio for two spoor gears is equal to omega in over omega out, which is equal to torque out over torque in. Where would you get this one from? This comes from the fact that you assume that the torque in times omega in is equal to torque out times omega out. And that is when you have basically power in equals power out. When the output power is the same as input power, that means your efficiency here is 100%. So if efficiency is 1 or 100%, yes, power in and power out are equal. There is no waste of energy. So these two are equal. So the speed ratio is also going to be torque out over torque in. So from here, your torque out, you can say this is equal to the speed ratio times torque in. This is for when there is an efficiency of 100%. Now, if there is no efficiency of 100%, then torque out omega out, which is power out, is going to be eta times power in, where eta is less than 1 this time. So there will be an eta here. So when you do that, now you're going to get an eta right down here. So when you cross multiply, that eta is going to show up and you get this formula. Okay, so if you know how much torque you apply to the worm, your speed ratio, which is the ratio of the teeth, and you know your efficiency based on this formula, guess what? You can multiply all of them together and see how much torque you can get out of the wheel or the gear, you might call. Now, because there is friction wear in worm and the wheel, you need to consider the following things. 1, make sure your worm is made of case hardened steel or carburized steel. Make sure the surface of the worm is very hard. For the gear, make sure it has great wear resistance, like bronze. And the other thing is, make sure you do a good job with lubrication to reduce the sliding contact. Something like extreme pressure additives, specific gear oils, can reduce the friction big time and bring that F number here, this guy, they can bring this guy down. Okay, so make sure when you pick worm gear and the lubrication, you do it for minimal wear and tear, minimal deformation, and the best case of friction that you can get, or minimal friction. Now that we have said all of this, let's look at one example together. So what does the example say? It says, in this case here, this is the worm, this is the wheel. The RPM of the worm is 1200, so this is a small n, this is a small n of W. wheel is supported at points A and B by two bearings. Okay. Let me see if I can move this a little bit. There we go. The power that is applied to the worm is only 1 horsepower. So this is that H parameter. How many teeth are on this active? How many threads are on it? 2. So this guy is N capital of W. It is engaged with the wheel that the wheel has 30 teeth. So this is the N of the G. The gear has a transverse diametral pitch of 6 feet. So this here, the 6 teeth per inch, this is diametral pitch, and diametral pitch is the number of teeth divided by the diameter of the pitch circle. So NG over DG for this guy is 6 over 1 inch. The face width of 1 inch. So the thickness of this guy is 1 inch. The worm has a pitch diameter of 2. So this 2 here is that D of W. And a face width of 2.5. So this guy here is 2.5 inches. The normal pressure angle phi n is 14.5 degrees. The material are such that use curve B to get F from this. So the material here for worm and the wheel are good material, low friction material. What do you need to find? First, find the axial pitch of the worm, which is Px. Find the center distance C. Find the lead and the lead angle, L and lambda. Then in this picture where the bearings A and B are supporting your gear, find the forces that are applied to bearings A and B. And also find the output torque, right? So you need T of G. And find the forces at the two bearings. Now here, if you look at the bearings, one of the bearings does not carry any axial load. One of them does carry an axial load. So for instance, this A could be like a ball bearing. This guy here is a bearing that can carry also some axial force. So this, for instance, could be like a taper bearing. Or if it's not a taper bearing, you might have some shoulder here on this shaft that rests against this bearing so it doesn't move. Okay, but one of them does have an axial load because the teeth apply axial load. And if you don't do it, your wheel is going to move in the X direction. And that's what you don't want. And this T is that TG that you need to find, the output torque on the system, right? The three forces that you have here are the radial force, the axial force, and the transverse force applied between the teeth of the gear and the worm. And these three guys coming from the actual W, the normal force, as well as the friction. Okay, so they are these guys. One of them is this, one of them is this, the other one is this. Okay, you can see them here. Where do you get your F from? F is going to come from that graph here. And it is going to come from curve B. So we are going to need this graph. And to use this graph, we clearly need to calculate these velocities. So first I need to calculate this, then plug it here, calculate Vs. Once I have Vs, then I go to curve B, and from there I can find my F. Okay, so I need to calculate all of these. Okay, so let's go ahead and start. First, we go with part A, find the axial pitch. Now, how much is the axial pitch of the worm? One of the things that I guess I just skipped it and I need to talk about it is right here, this line that I skipped. The axial pitch of the worm and the transverse circular pitch, PT, of the gear are equal if the shaft angle is 90 degrees. 90 means they are askew at 90 degrees. Okay, so when it says 90 degrees, it doesn't mean intersecting. They are still askew, but if you project them on the same plane, this angle is kind of 90 degrees. Okay, so here you can say that PT of the gear is the same as px of the worm. This is another one of those equations that can come down here. Okay? So that's the first thing we can use, is to say that, hey, for part A, px of the worm is equal to p, and this is a small p, pt of the g. And what was the definition of p? P is the circular pitch. And if you remember, the definition of circular pitch is pi d over n, so this is pi dg over ng. And this guy here is called gear modulus. The reciprocal of that is called diametral pitch. So another way to write it is to write it as pi over diametral pitch of the gear. So this guy here is 1 over diametral pitch. And how much was diametral pitch in the case of this problem? You can see that it was 6 teeth per inch. So if you simplify, you're going to get 0.5236. And it's going to be in inches, or inches per tooth, or teeth. Okay, so that's your first number. Then what? Then you need center to center distance, C. Remember, C was the average of the two pitch diameters, dw plus dg over 2. Do I have the two numbers? The answer is, well, dw is directly given to me, that's 2. dg is not given, but I can find it. Why? Because I have the ratio of n over d, and I have n. So from these two, I should be able to find d, correct? So let's go ahead and do that first. So before I do this, I need to first find the diameter of pitch for the gear. So I say ng over dg equals 6, and this ng is 30. So from here, dg is going to be 5 inches. So now this is like 2, and this is like 5 divided by 2, and you're going to get 3.5 inches, center to center distance. What else? Next thing is lead, L. How do you find L? L, if you look at the top, the formula was the number of threads times the pitch. Okay, the number of threads times the pitch. And the number of threads in this case is 2. If you look at it, that's 2. And the pitch I just calculated, that is 0.5236. So you are going to get 1.0472 inches. This is how much any point on the worm moves forward or backward when you rotate it 1 full revolution. Then it says find the lead angle, lambda. So if you remember, lambda was tangent inverse of the lead divided by circumference of the worm, pitch circle. So here I have this L, I just calculated it. dw is given to me somewhere, right? Let's see. That is a 2 also, so dw is 2. And plugging in and taking arctangent, I'm gonna get 9.46 degrees. One of the things I need to mention for you is for most of the worms, this lambda is typically a small angle, or the other way to say it is this psi here, which is 90 degrees minus lambda. This is typically a big angle. So you see, if I calculate psi in this case, it doesn't say you calculate it, but if I do that, it is going to be 80.54 degrees. Okay, so typically the helix angle is big, the lead angle is small. That is very, very common when you look at worm problems. So this is part one of this example that I went through for you. Now, part B, we need to look at the free body diagram and find the forces and everything. Now, if you remember, if I want to find the forces, first I need to find this coefficient of friction F. For that, I need to use this graph curve B. And to do that, I need the slide velocity. Before a slide velocity, I need to calculate the worm velocity of the contact point. So I'm going to use this formula, right? I'm going to use this guy right here, and I'm going to plug in numbers. So now I need to go to part B. As I said, I'm going to use this formula. Do I have everything in it? I guess I do, because this one was a 1200. Pay attention again that this number here is the RPM of the worm, not the number of teeth. So if you calculate this, you're going to get 628 feet per minute. Now this is V of the W. We need the sliding velocity. And if you remember, it was V of the worm divided by cosine of lambda. And lambda, we already calculated that 9 degrees, correct? So if I plug in the numbers, this is going to be 637 feet per minute. Now with this one and curve B on that graph, we are going to see what kind of coefficient of friction we are going to get from that graph. So if I go and look for 637, let's see if I can get something rough. Just do a fast cleaning. It's just a little bit too busy in here. So 637 is almost here, so that is 600, so something like that. And if you go up here on curve B and go down here, you see it's about 0.03. So here I can say that my coefficient is 0.03 for high quality material. Good. Now that I have that, I have F. What else can I do? So can I find my force components? Now I need to go and use these formulas. Yes? So now I need to go and use these formulas. Now these formulas, the problem with them is I don't have W in them. Okay, if you look at these formulas, there is no, they need a W, and I don't have W. But guess what? I can find Wt from this formula because I have the horsepower and velocity of the worm. So I can find the tangential component, which is the Wx. So I can find this guy. Once I have this, guess what? I can find y. How? Because if I divide Wy by Wx, then these two would cancel, and I simply get, for instance, sine of phi n divided by cosine of phi n sine of lambda, and then plus f times cosine lambda. And since I have Wx, and since I have the lambda, I have f, and phi n is given to me, I can find Wy. Then I do a similar thing. I divide Wz by Wx. Again, I'm going to get some similar fraction, which is going to be this one divided by that. And these W's would cancel. Again, I have Wx, all of that fraction I have. and I can get what? I can get WZ. So the first thing is I want to find my transverse force through that formula. So the transverse force for the worm is 33,000 times horsepower divided by velocity of the worm. Do I have the velocity of the worm? Yes, it's right up here. Do I have the horsepower? Yes, remember it was 1 horsepower. So if I plug in the numbers, this W of T is going to be 52.5 pound force. And remember, this is the WX. So now that I have that, guess what? I can either directly find W from here and plug it into the other two, or, as I said, I can do those ratios. So it's completely up to me. And you know what? Let me just use that ratio thing. So I'm going to copy this down here. And as I said, from here, I can tell you that WY is going to be WX times sine of phi n divided by all of that cosine of phi n sine lambda plus f cosine lambda. And I can say WZ is equal to WX times, again, the same denominator. Now the numerator is going to be cosine phi n cosine lambda minus f times sine lambda. And the denominator of that, as I said, is going to be that same thing. So I can copy that and paste it down here. Good. Now, do I have all the numbers? Yes. WX, I just found it. That's this number. It can go here and here. My normal pressure angle is directly given to me. It was 14.5 degrees. So this guy here is 14.5. My lambda was that 9 point something degrees, right? How much was it? It was 9.46. And this F that you have in a few places, this F, and this F, these guys are all 0.03 as we calculated. So guess what? I have everything. So from here, I should be able to calculate my WY and WZ. And if I do so, my WY is going to be 69.6 pound force. And this guy is going to be 264 pound force. There we go. So I got my WZ, I got my WY, and I got my WX. I got all three force components in this free body diagram. So now if I go back to this FBD, guess what? These three are taken care of, right? Because the radial one is equal to Y, the tangential, the transverse one is X. So here, this is X, this is Y, this is Z. I got these three guys. What is it that I need to find? 6 other components. What are they? The 2 forces at bearing A, the 3 forces at bearing B, as well as this torque. And this is a 3D problem, so I can have up to 6 unknowns, and by applying the 3 force equations and the 3 moment equations, I should easily be able to find them. The only thing is this. If I take some of the moment about any point and set it equal to 0, let's say point B, would the moment about point B, about the x-axis, would that also be 0 because the system is spinning about the x-axis? The answer is It is as long as the omega in the system stays constant. So since the omega input is constant, the omega of the will is also going to be constant, right? How much is it? Well, we can find it in this case, NG, NW over NG, the speed ratio, is equal to the basically number of teeth on the G over the number of teeth on the worm, right? This is the speed ratio. Again, pay attention, small n is RPM, capital N is the number of teeth. This guy is 30, this one is 2, this one is 1200. So you see the ratio is 15. So I guess it should be 80. So the RPM for the gear or the wheel is only 80 RPM. It has a reduction of 15 to 1. And this guy is constant. Because this guy is constant, the angular acceleration of the gear is 0. So some of the torque for it along the x-axis, which is the mass moment of inertia in that direction, that should also be 0, especially because this part is symmetric. Now, this is a 3D problem, but since the part is axis symmetric and alpha g is 0, you can say that the torque about the x-axis, about any point, right? If you say torque about point D, but in the x-axis, that should also be equal to what? Equal to 0, right? So I can say such a thing as well, because the system is not speeding up or slowing down. So then all you need to do, as I said, is 6 equations and 6 unknowns. First, the system does not move in any axis, so sum of these 6 forces is equal to 0. So you basically get WZ in the in this case, your WZ for the worm, for the gear, remember, it's the axial force. So WZ magnitude in the x-axis, and then WY in the negative y-axis, and then WX in the negative z-axis, plus these two plus those 3 equal 0. So you get 3 equations and 5 unknowns, right? And then what you need to find is the moments. So here you take some of the moments about point B, set it equal to 0. The only moment you have for B is t in the x direction. And the moment of these 2 forces about B and the moment of those 3 forces about B. Those 3 forces, if you want, you can combine them into a single force, call it W. And these 2 forces, you can combine them into a single force, call it FA. So when you take sum of the moments, let me add that for you somewhere. When you take sum of the moments about point B, you only need 2 position vectors. So for that, let me go down here and continue it down below. So I bring it down here. Let's see what I did. Okay, and I have those numbers. So 69.6 should be this one. The Z, which if you remember for the gear, look, for the gear, Z is the negative tangential. Okay, so the tangential for gear in the negative, and the negative is already considered here, that's your Z, and that is 264. And the axial is X, which is 52.5. Again, I combine all these 3 into a W. I combine those 2 into FA force, a 3-dimensional force. So I say sum of the total force on the system is equal to 0. In this case, it's going to be W. And then plus, or if I want to write it in terms of IJK, it is going to be 52.5 I, and then minus 69.6 J, and then minus 264 K. This is the W force. Then plus FZA in the Z direction, and plus FYA in the Y direction, and then plus FYB in the Y direction, and plus FXB in the negative X direction here, and finally plus FZ in the positive K direction. This is equal to 0. You see here, this is the X is in the negative X direction. So this gives you three equations. The I's are 0, the J's are 0, the K's are 0, right? So if I want to write those three equations, you are going to get 52.5 for the I. Any other I you see, you can add it. Minus FXB equals 0. So that should give you FXB. In the J, you have this. There is one more. Is it? Yes. And in the K, you have this. Okay, so the top one gives you FXB. The two bottom ones, they only have, each one of them has 2 unknowns, so you cannot solve. Then you take sum of the moments about point B and set that equal to 0. Now for that, you need to do this vector cross FA, and then this vector cross the W force, plus this T in the X direction that you have to add. So if you do that, it is going to be T in the X direction plus this vector here, which if you want to write it, it is going to be 1.5 plus 2.5, that's 4 in the negative I, so it's just negative 4I. Cross the FA force, and then this vector here, which has negative 4I plus 2.5 J, cross the W force, and W force are those three known forces. This is all equal to 0. So here you have, as I said, FZ A in the K direction plus FYA in the J direction. And here you have those three forces, these guys. Those guys are going to sit right there. Like that. And this guy, again, is going to give you another 3 equations, which, again, you can expand if you want. So you get another 3 equations for IJK. And now that you have 6 equations, 1, 2, 3, and then 4, 5, 6, that should allow you to solve for these 6 unknowns. One of them is this guy, 2 of them are these, and 3 of them are these guys. So 6 equations and 6 unknowns, and you should be able to solve for everything. And if you want the numbers, I have the numbers here. I can even give you the equations if you want. So let me give you the equations. So one of the equations is going to be like negative 52.5 times 2.5 minus, let me write them all. So these are the 3 moment equations if you write them. And then finally, if you solve from equations 1 and 2 and 3 and 4 and 5 and 6, you should be able to get all of these numbers. So T is going to be 660 pound force inch. Then FA, the Z component, is going to be 165 pound force. FA, the Y component, let's go with the same notation that we had. This is going to be 10.7 pound force. And then you can find the B ones by plugging them back into equations 1, 2, 3. So here you're going to get Fx at B, which is negative 52.5 pound force. And then Fy at B, which is going to be 58.9 pound force. And finally, Fz at B, which is going to be 99 pounds. There we go. So you get all 6 unknowns and you could solve this problem. Yeah, so it is quite a bit an involved problem. It involves a bunch of calculations, but hopefully you now have a better feeling about worms and the worm wheels or worm gears. Thank you so much for your attention, and I'll see you in the next video.